18 trillion tokens.
It's a number so big it almost completely loses its meaning, doesn't it? Until you stop and really think about what that represents.
That is the scale of data we are talking about today. And we aren't talking about OpenAI here, and we're not talking about Meta. We are talking about Qwen 2.5, which is the latest release from the Qwen team at Alibaba Cloud.
Right, and the mission for our deep dive today is actually pretty specific. We need to figure out exactly how a model that is significantly smaller, specifically their 72 billion parameter flagship model, is somehow managing to beat models that are 5 times its size.
It feels like we are finally hitting that point of diminishing returns with raw size, and Qwen just sort of found a detour. So for everyone listening today, whether you are a developer looking for open-weight models to run locally, or you're just tracking how fast this AI landscape is evolving, we're stripping this entire report down.
We really are, because usually in this industry, size is destiny, right? We have been trained over the last few years to believe that bigger parameters automatically equal better performance. But Qwen 2.5 is effectively breaking that rule. They are claiming performance that rivals Llama 3.1405B, which is a massive, massive model.
And they're doing it with a fraction of the compute. So we're going to look at the fleet they released, the massive data engineering project behind that 18 trillion number, and the specific post-training tricks they use to make the model smarter, not just bigger. Because the gap between proprietary and open models is basically vanishing.
It really is. And let's start with that lineup, because they didn't just drop one single model and call it a day. It is an entire swarm of models.
Yeah, they released a full suite of dense open-weight models. Everything from a tiny 0.5 billion parameter model, which, I mean, you could practically run on a smartwatch, up to that 72 billion parameter flagship. But I noticed they brought back 2 specific sizes that were missing in the last generation.
The 14B and the 32B are.
Exactly. Why those specific numbers? Is that just a random choice?
Not random at all, actually. That is a very direct nod to the developer community. It's entirely about GPU memory. See, there has been this awkward gap in the market for a while now. You have the 7B or 8B models, which are super fast and run on almost any laptop, but they aren't, super smart, they hallucinate, and they really struggle with complex logic.
And then you jump straight to the 70B models, which are great, but
a 70B model requires expensive multi-GPU setups. You're talking about enterprise-grade hardware or in cloud compute. But the 32B, that is the Goldilocks zone.
Because it fits on a standard consumer card.
Precisely. A 32B model fits comfortably on a single high-end consumer GPU, like an RTX 3090 or 4090 with 24 gigabytes of VRAM. It is powerful enough for complex reasoning and coding, so it feels like a big model, but you don't need to rent a data center to run it. They realized that if they wanted real grassroots adoption, they needed to hit that specific hardware constraint.
That makes a lot of sense. It is meeting the developers exactly where they live. Now, before we get too deep into the open weights, the report also briefly mentions Qwen 2.5 Turbo and Plus. These are API only, right? We can't actually download these.
Correct. Those are their proprietary mixture of experts models. The Turbo is positioned to fight GPT-4o Mini, and Plus goes right after GPT-4o. It is their way of saying, we have open models for the builders and managed services for the enterprise.
But honestly, the real technical innovation, stuff you and I can actually learn from today, is in the open weights. So let's get into the engine room. Pre-training. You started with that number earlier, 18 trillion tokens. For context, Qwen 2 was trained on 7 trillion. That is a massive jump.
It's more than double. But here is the catch. If you just feed a model 18 trillion tokens of the raw, unfiltered internet, you don't get a genius. You get a chaotic mess. The internet is full of noise repetition, broken HTML, and just low-quality arguments.
So how do you actually filter 18 trillion tokens? You can't exactly hire an army of interns to read through it all.
You use the AI to build the AI. They used their previous generation models, specifically Key 2, Instruct to act as a massive automated filter. They scored the new incoming data for educational value.
So if a piece of text didn't look like it would teach the model something useful, it just got tossed out.
Or heavily downweighted.
Yeah.
This ties into their whole data mixture concept. They realized that web data is heavily skewed. It is mostly e-commerce, social media, and entertainment.
Which is pretty useless if you want a model that can code a Python script or solve a physics equation.
Exactly. So they aggressively downsampled that generic web fluff and upsampled science, technology, and academic papers.
But there has to be a limit there, surely. I mean, how much high-quality PhD-level math data actually exists on the open web for them to scrape?
There's exactly the bottleneck the whole industry is hitting.
Okay.
We are simply running out of human-generated high-level data, and that is where the synthetic data comes in.
Well,
This is a huge differentiator for Qwen 2.5. They use spiralized models, specifically Qwen Math and Qwen Coder, to generate massive amounts of synthetic questions and answers.
Wait, walk me through that process. So they have an AI generating math problems to teach the next AI math. Isn't that like making a copy of a copy? Doesn't the quality eventually degrade?
It absolutely would if you weren't careful about it. But math and code are unique domains because they are objectively verifiable. If the AI generates a complex math problem and a solution, you can run a deterministic script to check if the answer is actually correct.
Oh, I see. So if the script says it works, it goes into the training set. If it's wrong, you just crash it.
Right. This allows them to create a customized curriculum that is far denser and much more difficult than what exists naturally on the internet.
So the model isn't just passively reading Wikipedia articles. It's essentially doing millions of verified homework problems that were custom designed for it.
Exactly. And that is how you get a smaller model to punch way above its weight class. It is simply better educated. It hasn't spent its compute cycles reading YouTube comment sections. It has been solving calculus problems.
Technically speaking, though, what is the actual architecture holding all this knowledge? Is it just standard transformer stuff under the hood?
Mostly, yes. They aren't completely reinventing the wheel here. They are just heavily optimizing it.
Huh.
They use rotary positional embeddings, which is pretty standard now for handling long contexts. But they also lean really heavily on GQA, which stands for Grouped Query Attention.
We hear about GQA a lot in these technical reports. Why is that specific piece of architecture so important for these dense models?
It is entirely about inference speed and memory management. In a traditional older attention mechanism, the model has to keep a massive amount of data in memory, the key value cache, for every single attention head of the model. It gets incredibly heavy very quickly.
So it eats up all your VRAM.
Right. What GQA does is it groups those heads together, sharing the cache across multiple heads.
Which significantly reduces the memory footprint required to run the model.
Massively. And for a 72B model, that is crucial. It means the model generates text faster and uses less VRAM, which goes right back to that main goal of making these things actually usable for developers on their own hardware.
Okay, so we have a model trained on 18 trillion tokens of highly curated, partly synthetic data. Now we move to post-training. This is the really fascinating part where we turn the raw intelligence into an actual helpful assistant.
Right. This is the alignment phase, moving from learning to speak to learning to behave. And the scale here is also huge. They used over 1 million examples for supervised fine-tuning, or SFT.
Usually this is where companies hire thousands of human annotators to write out good and safe responses. But Qwen seems to have automated a lot of this step too.
They had to. The sheer volume is too high for humans. They leveraged those large-scale synthetic data sets, again, especially for coding and math. But the most interesting part of the SFT phase to me was the multilingual transfer.
Yeah, I saw that in the notes and wanted to ask you about it. They claim it heavily boosts performance in low-resource languages. How does that actually work in practice?
Well, think about where the absolute best training data is currently located. The best coding tutorials, the best logic puzzles, the deepest Stack Overflow discussions. They are overwhelmingly in English.
Right. English dominates the technical web.
So if you only train your model on native Indonesian data, for example, the model might speak perfectly fluent Indonesian, but it's going to be terrible at writing Python or doing complex logic.
Because the Indonesian data it learned from didn't have those complex coding examples.
Exactly. So what the Qwen team did was take that high-quality English instruction data, and they used translation models to adapt those prompts and answers into languages like Indonesian Arabic or Thai.
Oh, wow. So the model learns the underlying logic from the original English example, but it learns to express that logic in the target language.
Precisely. It actively prevents the model from being a genius in English and a toddler in other languages. It bridges that gap and transfers the reasoning capability across the language barrier.
That is incredibly smart. It separates the cognitive thinking part from the vocal speaking part. Now, after SFT, we get to reinforcement learning. The report breaks this down into offline and online RL. Can we clarify the difference between those two?
Sure. Offline RL is a bit like grading a test after the student has already left the room. They use a technique called DPO direct preference optimization. They basically take the model's generated outputs, run them through automated verifiers. Does the code actually compile? Is the math answer correct? And then feed that preference data back into the model to update its weights.
So that's for the purely objective stuff. Math is either right or wrong. Code either runs or it throws an error.
Right. Online RL, on the other hand, is for the subjective stuff. Things like tone safety, helpfulness, conciseness. They use a separate reward model to actively judge the model's responses during training. But they used a specific optimization method here that I think is really clever called GRPO.
GRPO, Group Relative Policy Optimization. Sounds like a mouthful. What makes that different from standard reinforcement learning techniques?
Standard RL can sometimes be really unstable. Sometimes the model learns the exact wrong lesson from a reward. GRPO focuses specifically on high-variance queries.
High variance meaning what exactly?
Imagine you ask the model a really hard logic question, and it generates 5 different answers internally. One of them is absolutely brilliant, and the other 4 are complete garbage. That is high variance.
So the model is confused, basically. It's just guessing and hoping one hits.
Exactly. It stumbled onto the right answer purely by luck. What GRPO does is it targets those specific confused moments and forces the model to converge its policy toward that one brilliant answer. It essentially stabilizes the model's performance on the tricky edge cases where it isn't quite sure of itself.
That is a great way to think about it. It's like a basketball coach watching a player make a crazy lucky shot and saying, okay, I need you to do exactly that again, but do it on purpose this time.
That is a perfect analogy. It builds consistency.
Which brings us perfectly to the actual results. We have built the brain, we've specialized the training, we have aligned the behavior. How does this thing actually perform out in the wild? The headline comparison everyone is talking about is Qwen 2.572b versus Llama 3.1405b.
And this is where the entire industry's jaw drops just a little bit. Let's look at the math benchmark. Qwen 2.572b scored an 83.1. The massive Llama model scored a 73.8.
That is not a small margin of error. That is a decisive knockout win for a model that is effectively 5 times smaller in parameter count.
It completely validates their entire synthetic data strategy. It proves mathematically that you do not need 400 billion parameters to do complex math if you have been trained on millions of high-quality synthetic math problems. The specialized curated training simply beats raw generic size.
What about coding? Because that is usually the other big metric developers care about.
It's a very similar story, though, a bit closer. On the human evil benchmark, Qwen scored an 86.6. Llama was at 89.0, so Llama technically wins there, but barely. We are really just splitting hairs at that point.
But we certainly aren't splitting hairs on the cost to run these things.
No, not at all. For a developer or a startup, the difference in coding performance is basically negligible, but the compute cost to run Qwen is exponentially lower. You're getting 98% of the performance for maybe 20% of the hardware cost.
And we really have to mention the 32B model again here. The report explicitly calls it the pound-for-pound champion of this release.
Justifiably so. The Qwen 2.5 32B model is actually outperforming Llama 3.172B in many of these coding and math tasks.
So a 32 billion parameter model is beating a 70 billion parameter model. That is just ridiculous efficiency.
That is the Goldilocks effect we talked about earlier playing out in the benchmarks. It's optimized so incredibly well that for 90% of actual real-world use cases, you honestly just don't need the bigger models anymore. The 32B is rapidly becoming the new default standard for local development.
Even the tiny ones, the 0.5B and 1.5B, they're looking surprisingly usable.
They are massive upgrades over their own previous generation. And this completely opens up the door for truly capable on-device AI. Imagine having a highly competent language translator or a basic coding helper running locally on your phone while you are in airplane mode without any internet connection. That is what these small, dense models enable.
That is wild to think about, your phone just getting fundamentally smarter without ever needing to ping the cloud. But let's pivot to something that plagues basically every LLM user right now, context length. It is great if the model is a genius, but if it forgets what I told it 10 minutes ago, it is virtually useless for long tasks.
Context is huge. Qwen 2.5 standardized on a 128K token context window across the board for all the models. That is roughly a novel-length amount of text. But the Qwen 2.5 Turbo model pushes that up to 1 million tokens.
1 million tokens. That is an entire application codebase or a massive legal archive. But does it actually work? Because we have seen other models claim these huge context windows, but then they just get totally lost in the middle. They completely forget the specific details buried in paragraph 400.
Right. That is the infamous lost in the middle phenomenon. To actually prove this works, they ran what's called the passkey retrieval test.
Oh, I love this test. This is where they hide a random number, a passkey, in a massive pile of irrelevant text, right?
Exactly. They hide it 1 million tokens deep in a document and ask the model to pull it out. Qwen 2.5 Turbo hit 100% accuracy on that test.
Okay, so it can successfully find the needle in the haystack. But processing a million tokens must be incredibly slow. I mean, traditionally, the longer the prompt, the slower the time to first token.
It absolutely would be without a mechanism they implemented called sparse attention, or as they call it, minference.
Inference. I actually really like the branding on that, but how does it function technically?
Think about how you or I skim a very long document.
Mm.
You don't give every single word on the page equal mental attention. You scan for keywords, you read the headers, and you focus your brain power on the relevant sections while blurring out the rest. Sparse attention does something very similar mathematically.
So it dynamically identifies the relevant blocks of text and it just skips the rest during the calculation.
Right. It isn't wasting precious compute cycles on the filler words. The report notes that this speeds up long document processing by 3 to 4 times. It turns that 1 million token window from a purely theoretical marketing feature into something you can actually use without waiting 10 minutes for a reply. Speed is a feature.
Speaking of usable features, one detail in the specialized skills section really caught my eye. Structured data. They explicitly state they train the model heavily to understand and output JSON and tables. Why carve that out specifically?
Because this is a massive, massive pain point for software developers.
Mm-mm.
You ask an AI to return a list of user data, and instead of giving you clean code, it gives you a conversational paragraph. Or worse, it gives you the JSON, but it misses one single comma, and it completely breaks your entire application pipeline.
Right, it just crashes the app.
The Qwen team realized that for these models to be deeply integrated into actual software systems, they need to speak machine language just as reliably as they speak human language. So they aggressively trained it to be robust with JSON formatting tables and strictly structured outputs.
So you can actually trust it to be a reliable back-end component, not
Yeah.
just a chat interface.
Exactly. And alongside that, they also heavily stress-tested it with system prompts.
Those are the hidden instructions that tell the AI who to be and how to act right.
Right. And typically, if you give a model a very complex persona,
Mm-hmm.
like you say you're a grumpy pirate who only speaks in riddles and is teaching advanced calculus, sometimes the model breaks character or its actual math ability plummets because it's focusing too hard on the pirate voice.
It gets distracted by the role play.
Right. So they trained on hundreds of incredibly diverse system prompts to ensure the model stays firmly in character without losing any of its baseline IQ points.
Looking at the very end of the report, the future directions section drops a pretty massive hint about something called inference compute scaling, which to me sounds a whole lot like what OpenAI is doing with the O1 model.
It absolutely does.
Yeah.
They're talking about the industry-wide move from fast thinking to slow thinking. Currently, most models just predict the next word almost immediately. Inference compute scaling means the model would essentially generate internal thoughts or reasoning steps to verify its own logic before it actually prints the final answer for you.
So the model effectively pauses to think it over.
Exactly. The report strongly suggests this is the very next frontier they are tackling, integrating that deep, deliberate reasoning process directly into open weights.
Bringing this all together, it really feels like Qwen 2.5 is a huge maturity moment for open-weight AI.
It really is. It decisively proves that the defensive moat around proprietary models is evaporating fast. You can literally download a model today for free that rivals the very best closed systems in the world, provided you have the hardware to run it.
Mm-hmm.
It fundamentally shifts the power dynamic from a few giant tech labs back to the broader developer community.
But before we completely sign off, there was one highly philosophical nugget buried right at the end of the report that I found genuinely a bit unsettling. They talked about a broken yardstick.
Ah, yes. The reward model problem.
Yeah, they noted that their reward models, the AI judges that they use to score how good an answer is during training, were handing out high scores, but those high scores didn't actually predict that the model was learning the right underlying concepts.
It is a classic textbook case of Goodhart's law. When a measure becomes a target, it ceases to be a good measure. They're openly admitting that the automated tools we use to evaluate AI might be losing their effectiveness at these higher levels of reasoning. We are effectively optimizing for the test score, not necessarily the actual intelligence.
Which is a pretty heavy thought to end on. We are building these faster, smarter engines, but our speedometer might actually be broken.
We might be optimizing for the exact wrong things without even realizing it. It is a significant technical risk as we push into this next level of artificial intelligence. Because if we can't accurately measure what better is anymore, How do we know we are actually going in the right direction?
Something for you to definitely chew on while you are downloading those 18 trillion tokens worth of knowledge to your local machine. Thank you for taking this deep dive with us into Qwen 2.5 today.
We will see you next time.